这样就拍摄。我没有，他们说就是5分钟之前最好先按下去，反正就是因为怕会忘记，因为之前都有忘记。
morning. The first lecture of this morning will be given by Professor Xue Qikun from National Tsinghua University. The title is Experiments on Topological Insulators and Quantum Anomaly Hall Effect. Let's welcome Professor Xue.
Thank you very much for the introduction. In this, I think this is the first physics summer school on topological insulator and spintronics set by we call the pioneer, right? In this school, I like to talk about this experiment on topological insulator. And in the later part of my talk, I will focus on this quantum anomalous Hall effect. So mainly the experiment we did to achieve this effect by using the magnetic topological insulator. I'm from the Department of Physics, Tsinghua University. So this is the outline of my talk. And first, I like to talk about give you some introduction, particular Hall effect and quantum Hall effect. Then I will talk about the topological insulator and mainly focus on the experimental part, particular MD groups and characterization by the photoemission spectroscopy. I think in this summer school, you already heard many particular theoreticians about the idea and the concept of the topological insulator. For that reason, I will not go to the detail and focus on the experimental part. And then, starting from the fundamental materials, the basic materials prepared by the MD, we realized the magnetic topological insulator with exhibit the ferromagnetic ordering and also the insulating. And then with that kind of materials, we realized this quantum anomalous Hall effect. Finally, I will give some perspective of this particular direction. I think for most of you, the major in physics, you know this very famous Hall effect, which was discovered 130 years ago in 1879. So as you can see from this figure, we have this certainly is the two-dimensional, but this thin film or this very thin conductor. If you put the current along from the left to the right, along this direction, you have the current flow. Then if you apply the magnetic field in this direction, then you will see some of the charge accumulation in both sides of this conductor. And if you measure this charge accumulation, you get the voltage. That is called the Hall voltage. And if Hall voltage divided by this current flowing along this direction, you get that's called the Hall resistance. So Hall, is actually the relationship between the Hall voltage and the current magnetic field and other parameter of the materials. Like the N here is the carrier density of the materials. The T here is the thickness of this plate, and the E of the charge of the electron charge. So by this very simple measurement, we can get many very important parameters of the material, like the carrier density and the mobility. This is very important, particularly for the semiconductor industry. You have to know what kind of mobility your materials. Use this material, you make the transistor. This mobility will affect the performance of the material very much. In the experiment, if you draw the Hall resistance as a function of the magnetic field, you get this, this straight line. So it means the Hall resistance is proportional linearly to the magnetic field you apply. So this is a very simple curve. You understand. This is also the very easy experiment to do. This is the very famous Hall effect. And as you know, the Hall effect has a lot of applications already you see in your daily life, like this speed meter and this current measure, and also this all these things you know that's made by this Hall detector. So if as long as you have a small magnetic field and you can detect this magnetic field by this some calculation to the quantity you want to measure, then you get this kind of application. So also now we use the mobile phone and other things. Anything can be automatically controlled by this Hall effect, Hall detector using this very famous Hall effect. So this is show the wide application of Hall effect. So probably you know, I don't need to go to the detail. And the Hall effect is related to non-magnetic materials. So here we need the magnetic field. If we use a magnetic field instead of the non-magnetic field, since you have the internal magnetic field, so they may have the similar effect to the flowing charge of the electron and the Hall. They may also, without any magnetic field, by the internal magnetization, you can also get the Hall effect. So that's actually was done by Hall 1 year later, and then measure this side and this side. The voltage is just see this kind of the curves. So the Hall resistance and the function magnetic field is much complicated. This linear dependence with the non-magnetic field materials in the Hall effect, because this will reflect the very complicated property of magnetic materials. But basically, this internal ferromagnetization or magnetization look like probably the similar effect as the external magnetic field. But actually, the understanding for the mechanism for this Hall effect called the anomalous Hall effect. One of the reasons we call the anomalous because the mechanism is very difficult to understand. And so after the discovery of this anomalous Hall more than 130 years, still we have some argue on the mechanism for the anomalous Hall effect. Basically, there are three theoretical proposals to explain the anomalous Hall effect. So the first one we call the intrinsic mechanism, proposed by the Calculus and Latinger in 1954. Here, the theory proposed that the spin orbital coupling in this magnetic material is the main reason, the mechanism for the Hall, this anomalous Hall conductance or resistance. So in this case, the Hall conductivity is proportional to the conductivity along this longitudinal direction. And there are also two internal mechanisms. The first is the skew scattering. That is proposed in 1958 by Dr. Smith. And the skew scattering comes from the impurity of the materials. So that's why we call the extrinsic mechanism. Because your materials have some defect or impurity, they can cause the skew scattering. Then you can get this Hall resistance along this along the direction perpendicular to the charge flow direction. Another one also related to impurity or this non-perfect materials, so-called the side jump, proposed in 1970 by the Dr. Berger, probably in the figure B. So in this case, this conductivity proportional, rho x square, and in this case, just the linear proportional to the rho x. So in this case, by consider 3D mechanism, you can have this kind of a relationship. So right now, we have know the final answer for the mechanism of the anomalous Hall effect. Although most of people think the spin orbital coupling is the main mechanism. So in 2009, there is a review paper published in the Review of Modern Physics. Professor Nagata from University of Tokyo, and Tsinghua from the same Texas A&M, and Onoda from this Riken, and Professor McDonough from the UC Austin, and Professor Ong from the Princeton University. They together write this review paper on anomalous Hall. In the last part of this paper, future challenge and perspective is rated several very important sentences that a major challenge for the experiment is to find examples for quantized anomalous Hall effect. So means if you can to realize this quantized anomalous Hall is very important for understanding of the mechanism of anomalous Hall effect. And you can see here, they also say such a finding will be the ultimate achievement in identifying intrinsic anomalous Hall effect. Means as once you observe this quantized anomalous Hall effect, then in this case the material will become the complete insulator, and there will no impurity or the intrinsic mechanism related to this skew scattering or side jump. So you can safely conclude the mechanism for the anomalous Hall effect will be the spin orbital coupling mechanism, which is intrinsic without consideration of this impurity. So this is this paper indicates if the importance of observation of quantized anomalous Hall effect. So I just give a very short review of the ordinary Hall effect. So there is a big development in this direction in the 1980. I think many speakers maybe already might already talk about this one. So Professor Qikun and Max Planck Institute measured use this sample of the silicon MOSFET. Means use the sample made by this silicon and the silicon dioxide interface, where the carrier, the electron or hole, confined in the two-dimensional at the interface, and they measure the Hall effect at low temperature and high magnetic field. They have the two surprising discoveries. Firstly, the Hall resistance exhibit a quantum plateau within the such range of magnetic field applied. There is no change in the Hall resistance. So as I mentioned, Hall in the normal conductor, the Hall resistance is a linearly proportional magnetic field. There is a very straight line I just showed you a moment ago, but now you at such a magnetic field range, you have no change in the resistance. That's very strange, very surprising. The second surprise is the Hall resistance is quantized in a value of such physical constant like the Planck constant, and divided by E square. E is the charge of electron, and then divided by the integral mu here, 1, 2, 3, 4. So this is another surprise, because these results indicate that the physical property of these materials, the transport property of in this system, look like have no any relationship with the materials you studied. So this is the second fascinating phenomena in this. The phenomenon is fascinating because those kind of results is indicative of the device size and geometry, and also the materials you use. So this is second. So of course later on in 1985, Professor Qikun Xue received Nobel Prize because of this great discovery. And another thing is 2 years later, Danny Tui and also Storm at the Bayer Lab together with Gosar and measure the different two-dimensional electron system, use this gallium arsenide, aluminum gallium arsenide two-dimensional electron gas, where the difference between this sample and the previous sample is the mobility in this case is much higher than the silicon dioxide interface where the electron mobility is much lower. Here, now I think the record, the mobility for good sample can be go up to the, I think, 20 or even higher, 20 million mobility. So in this case, they observed even the quantum Hall recipient appear in this fractional value. So of course later on, Bob Laughlin at Stanford University explained this kind of thing, and they together received the Nobel Prize in the 1998. So this is so from Hall to quantize the Hall effect. There we have the integral quantum Hall effect and also have a fractional quantum Hall effect. So as an experimentalist, to me, this discovery is so important because since the discovery of this quantum Hall effect, regardless of the integral and the fractional quantum Hall effect, physics basically go to the two directions, or there are two aspects in the materials. The first, usually if you measure the property of a system, that's you change the materials, you change your geometry, you change the size of your system, then of course the thing will be changed. The measurement of the results will be changed. Like the superconductivity, if you change the materials from one to another, then you get the different transition temperature, you get the different critical current, and also the magnetic material, same thing. If you change it from one to another, you get all the magnetic, the hysteresis and the saturation field, and all the things will be changed. So this is, of course, can be explained by the Landau symmetry breaking theory. And as I just mentioned, another aspect in this, after the discovery, so we have some kind of property or the measurement which can give us some results. These results is nothing to do with the individual materials. So it's independent of the materials and geometry you studied. So now I think a lot of theoreticians in this summer school explain this. We have no symmetry breaking here. This later on a topological concept came out. But basically, let me just summarize this very simply about this Hall effect. In 1879, Hall discovered this Hall effect by using the magnetic field in a very thin plate of a conductor. Later on, the confinement really the two-dimensional, and Hun Collision discovered the integral quantum Hall effect, and Daniel and Stormer and Bob Laughlin discovered this and explained the fractional quantum Hall effect. So in this column, basically we need this external force magnetic field to have this kind of effect. So as I just mentioned, in 1 year later after discovery of Hall effect, Hall used this magnetic material discovered this anomalous Hall effect where we don't need any external magnetic field. So the question, if you compare this column, immediately is that whether we can observe the quantized anomalous Hall effect. In this case, of course, we don't need any external magnetic field. So you can very easily imagine if we don't need the external magnetic field, we may use this quantized Hall effect to do this develop some less power consumption electronics, because the longitudinal the resistance along the sample is basically zero when you have this quantum plateau. So it means the power consumption for the longitudinal transport will be low, will not cost any energy. So this is very important. So this is the question whether we can realize the quantized Hall effect without the application of external magnetic field. So this is some of the, from this historical review, we have this question. Of course, everybody know we last year around I think October or November of last year, we see the first evidence of this quantization anomalous Hall eventually after we complete all the experiment in the end of last year, and eventually the paper published in April the 12th. So the title of this paper is the experimental observation of quantum anomalous Hall effect using this magnetic topological insulator. So after the publication of this paper in the same issue, Professor All at Rutgers University in US wrote a paper titled the complete quantum Hall trio. So the trio means this is one of the trio from the Hall to the quantized Hall effect is one trio. Also in the 2004, they theoretically proposed and realized this spin Hall effect. And in 2007, actually 2006, So Tsinghua and Stanford University proposed to use the two-dimensional topological insulator for the quantized spin Hall effect in collaboration with Professor Mollenkamp at Germany in the 2007. They reported the quantization of the spin Hall effect. So from the spin Hall effect to the quantized spin Hall effect is another of the trio, and the final one is this from the anomalous Hall effect to the quantized anomalous Hall effect. So by using this new concept materials, magnetic topological insulator. So I'm sorry, I didn't realize I have to give a talk in English, so I just use this. So I just want to mention, acknowledge our team working on this experiment. So basically, this team consists of the two parts of the experiment. One is the material growth. I'm sorry for some of the audience couldn't read the Chinese. And this material growth and the characterization on the electronic structure. My own group at Tsinghua University, Professor Chen Xi, and Dr. Ji, and Professor Jia now moved to Shanghai Jiaotong University. They also, we still have a very strong collaboration. My previous group and the Institute of Physics, now the group leader is Professor Ma Xutun, and together with the two younger researchers, Dr. He, actually he later on, particularly for the quantized anomalous Hall effect, he is the main person for the sample growth. And also for another part of the experiment is the low temperature strong magnetic field transporter. This is mainly done by the Professor Wang Yayu's group and our department. We prepare the sample, we characterize the sample. Once we see the sample is good, we transfer the sample to the Professor Wang's group and do this transport method. So we have actually from the material growth to the characterization of electronic structure to the transport method, we have very harmonic and strong collaboration. That's, I think, very essential for the final realization of a quantum anomalous Hall effect. Later on, because our sample still not the ideal, still have the sample contain some of the bulk, electronic states. We need a lower temperature. So for that we collaborate with Professor Li at IOP. His group is great in the low temperature physics. They can reach the measurement temperature down to 30 or even 20 millikelvin. At this temperature, we can kill all the contribution from the bulk trivial electronic